very happy to have with us today Professor José Moura from CMU. And Professor Moura is a university professor at CMU, where he has a very distinguished career. He founded the Center for Sense Critical Infrastructure Research and the Information Communication Technology Institute. The latter is a very innovative program within Portugal and CMU in areas of systems, communications, control, and security. He is a director-elect of the IEEE, and he was president of the IEEE Signal Processing Society, and he was editor-in-chief of the IEEE Transaction Signal Processing. And he's a member of the board of IEEE Proceedings and the ACM Sensor Journal. So he's a fellow of the IEEE and a fellow of the American Association for Advancement of Science. He is a corresponding member of the Academy of Science of Portugal. And he received the IEEE Signal Processing Society 2010 Technical Achievement Award. He's going to talk to us today about Kalman and Kalman-Bucy at 50, meaning 50 years after it was discovered, distributed and intermittency. So, Professor Moura, welcome.
Thank you very much. It's a pleasure to be here, and thank you for inviting me. This is my picture when a few years ago. You look younger. Yeah. Yeah. So this is my former student. I have to be careful. Former student, Shomokar, and of course this is work. What I'm talking about is based on a long-standing collaboration with Shomo. Shomo spent a year at Princeton as a postdoc, and now he's back at CMU as a faculty. And of course, we also have to acknowledge the sponsors, and the sponsors are listed there. Okay, so I will go through some brief historical remarks because I think that in fact last year and this year, at least for people like me, and I'm sure people like John, we really appreciate what Kalman and Kalman-Bucy did a few years back. I could say that without them, maybe I would have a career, so why not acknowledge them? And I think it's a great. So I'll go over and remind you of what you will know. Then I'll go through the specifics of the work I want to talk about. And it's all derivatives of consensus and how you go a little bit beyond consensus. And then I'll tie back to Kalman and Kalman-Bucy as we go along. So let me get started. It's interesting that 2011 is 50 years after 1961, but it's also 70 years after 1941. And if you go back in history, 1941 or thereabouts, 1939, 40, 41, 42, it's actually two major advances also in the area of extracting information and signals from noise. Kolmogorov, which really, if you look at the work of Kalman, Kalman really the roots I think go back to Kolmogorov rather than Wiener, since they took very different paths to the solution. So then you have the work of Wiener, and which is around the same time. And the interesting thing also is that the solution to Wiener is 8 years after 1931, because Wiener did realize when he was working on his time series analysis, extrapolation, interpolation, smoothing, he did realize that the solution was in terms of some filter of the observations, and the filter was given by the solution to a problem he had solved with Hopf 10 years earlier. So it's like 50, 70, 80. So it's a nice experience. Now, I couldn't resist and put here the yellow peril, which is the name by which Wiener's work was known at that time. And any $17,500 will buy you this unique copy of the 300 that apparently were made. Okay, so if you want really to get a hold of this, rush, because there is only one copy on sale. And it's not me that's telling you. Anyway, the yellow period is kind of a myth I had never seen, but when I started preparing for this talk, for some reason I came across it and I said, oh gee, it might be interesting to share it with everybody. So anyway, here is the original paper, or a cover of the paper, 1960. For those of you, I know that ISR is a highly interdisciplinary center, so, but for electrical and computer engineers, okay, we would like to have Kalman publish their work in our journals. That's not the case. It was published in the mechanical engineering area. I don't know really why, but that's where it's published. And that's this paper is 1960, so March 1960, and then 1 year later exactly, you get on the same journal, Mechanical Engineering, the paper by Kalman and Bucy. Now, you can see, don't be fooled here by the photos, okay? This is a photo of Kalman, I guess, a couple of years ago, and this is the photo I got actually from the Controls magazine.
You forgot to mention the most important part of this slide, that this paper originated in Mellon, right?
Okay. Yes, right.
Ryan was an exception to that.
Yeah.
Martin Marietta has set up in Baltimore,
Yeah.
and Bucy was at the Johns Hopkins Applied
Right.
Physics Lab.
Yeah. Yeah, there are some tidbits of history we could expand both on Reyes, on the Okay, so one thing I also want to note is that Kalman, when he wrote his paper, there are two things. If you go back through the paper, there are two interesting facts. One is that he says he's solving the Wiener problem. Okay, that nobody nowadays says that he didn't solve the Wiener problem. He present an alternative solution to the maybe identify this time series problem as the Wiener problem. The other thing that is interesting is that nowhere in the paper does Kalman mention the word Riccati. Okay, the word Riccati does appear on this paper. Okay, and again, we could go over some interesting tidbits there. So let me just remind you of what the solution of the problem is and the solution that Kalman-Bucy, and this is taken from the Kalman-Bucy paper. And very quickly, you have a centralized system. That's the basic thing I want to say. It's a centralized system, so you have some dynamics. So the plant or the signal follows some dynamics, and you have some noisy observations. And then the solution replicates the dynamics. You see the same F here and there. Okay, so you have your estimator, your filter, and it goes, and then there is a gain, and that gain involves the covariance, the error covariance, and this is the Riccati equation here in continuous time. I'm going to address discrete time later, and this object in the second part of my talk, that's the object I'm going to focus on. And but the point here is that it's a centralized solution. Okay, obviously that was the problem. And the structure is you have a prediction part that follows the dynamics, as I said, and then you have the innovations part, which is this, that is like measurements, current measurements minus the current estimate of the measurements, and then you have a gain. Okay, and I'm just reinforcing this because later on I'll try to come back to this. And the other important thing that Kalman's work did is that he said, well, this object here is going to behave well under certain conditions, okay? And so when we go to the distributed setting, we'd like to have similar conditions. So when we go to the distributed, here is what I want to focus on. I want to focus on sensors, agents that spread over some geographic area. They have local interactions, which means that they don't have interactions of one-to-all, but one-to-neighbors. And there is no centralized solution, meaning that not everybody sends all their measurements and all their current knowledge to some centralized location, a fusion center. So this is not the centralized version of the problem that had access to everything everybody's doing at the same time. So the solution is going to be a cooperative solution. By cooperative simply means that the sensors or the agents are going to talk to each other, and then they are going to iterate and they progress over time. In the first part of the talk, there is only one snapshot available, meaning that the agents, the sensors measure the environment, and then they don't measure the environment, and then they progress iteratively. In the second part of the talk, we are going to see an interplay between this cooperation between the sensors and the measurements that they make from the environment. And because this may be very large and very large number of sensors, very large area, we have to assume that things are not always correct. The communications might be through packets, and packets may drop and fail. So these links here, they are random in themselves. Okay. There is noise, of course. There is bandwidth restrictions, so you might have quantized communications, not real numbers floating around as they communicate. So there has to be, when we address these problems, there has to be some realistic assumptions that come from the distributor. And even the sensors themselves may fail, okay, may be intermittent, and maybe sometimes they are available, sometimes for some reason they are not available. So that's what I mean, a distributed solution has to take care of these complications. Okay, and the other thing I want to note is that when you go to a distributed solution, at least in our work, we don't claim to look for an optimal solution. What we claim is to offer some guarantees asymptotically regarding performance. We don't say that at every time step we have the optimal solution. So we may present to you an algorithm, and you may be much smarter, and you come back with an algorithm that performs well in the finite horizon. Okay. So what we are saying here in this work is only concerned with the asymptotics. Okay. So when we talk about optimality, it means that it's after the system evolved and iterated and cooperated and did all sorts of things. And of course, then the other thing, besides being asymptotically with nice properties, then what you also want is that the rate at which the system is converging to those nice properties asymptotically is also very important. So usually, optimality for me means these two things. Okay, let me remind you very quickly of the class of distributed algorithms that our work falls into, and falls into these class of averaging distributed cooperative algorithms, that is consensus. Just to remind you quickly, so each of these agents or sensors has a state. The state means their current knowledge. Okay, if we are solving an estimation problem, it's their current estimate. And so when we call that the state, so this is the state of sensor 1, that's the state of sensor capital N at some time I. And very often, rather than presenting the equations for a particular sensor, we may present equations for the collection of all the states of all sensors or all agents. But that doesn't mean that when we write an equation like this, that this is a centralized algorithm. Okay, what this means is that I collected the capital N equations for the states, for all the individual states, and each of the equations for each of these microstates here is only going to involve their own state and the state of the vectors. Okay, so what that means is that these matrices here are highly sparse. So, okay, this is consensus, and in this very simple setting, all there is an issue of convergence. So how does this converge? And that depends on the pattern of connectivity of this network here that is embedded in this matrix here that is called the graph Laplacian. And as long as it turns out this is a positive semi-definite, you order the eigenvalues from smallest to largest. As long as the first non-zero eigenvalue is strictly greater than 0, actually that's the second in the ordering of the eigenvalues, as long as it's strictly non-zero, this graph is connected, and that's enough for this to converge. So that's all you want. Okay, so consensus goes back to this, and the convergence is going to be exponentially fast. And they converge to the average of their measurements. So this is the case where you only have a single snapshot, and then you iterate, and as long as this condition is satisfied, which means as long as this is connected, then this goes, and here are some historical papers. This all started with work at CCP about 20.
So everybody learns about the average value, initial value.
Yeah. Everybody learns the average of the initial value. Okay. So if I have 1 and you have 3 and he has 5, we iterate and eventually we all come up with 3.1 plus 5 and 5.3. Okay, so now we want to go to a slightly more complex environment, as I told you, but still in the context of no additional measurements. What I put here is how you have to change the consensus algorithm. So what we had before was simply this xi, this li, and xi. But now, if you bring random links, this L, which is the Laplacian, becomes a random matrix. So you can, if you don't want to think of the Laplacian, think of the adjacency matrix of the graph, and the ones in the non-zero entries of the adjacency matrix, which means where you have links, they become now Bernoulli variables. Okay, sometimes they are up, sometimes they are down, and so this becomes random. Depending if you have quantized communication or you have noise in your communication, you have an additional noise term there. And the structure of the algorithm that we analyzed is you look at this and you simply say, okay, now when I communicate, okay, when the sensors communicate, sometimes the communication doesn't go through because the packet is dropped. So where there was a 1 maybe here, that became a 0 because it's Bernoulli at some time I. So the communication does go through, and when the communication goes through, you do have some noise there. And the other thing is, for this to have nice properties, then you have to weight this with some alpha, and these are standard conditions in the stochastic approximation type literature. And essentially, all you have to prove now convergence, you have to go, first of all, to understand convergence to what, okay, convergence to what. Because of all the randomness, you cannot expect convergence to the average of the initial snapshot. Okay, so you have to reinterpret convergence, and convergence now is to a random variable, but everybody converges to the same random variable. But as a random variable doesn't mean that everybody converges to the same number. Okay, they converge to a random variable, but that random variable is unbiased and has a variance, and under certain conditions, you can actually put a bound on the variance of that random variable, and here is the number of links. The number of links if they were all up. Okay, if they were all up, the number of links in what we call the supergraph, meaning that if there was no structural noise, if the links available were up, you'd count. It's not for the complete graph, it's for the sparse graph that you have. And P is the probability that the link is up or not. So you kind of get this. And these alphas, as I said, satisfy these conditions. So this is finite here. But if you, then there is the usual trade-off in these types of algorithms, that if you make the alpha i's to go very quickly to 0 or not, you have a trade-off between, well, essentially you slow down or not the rate of convergence, but this is exponential rate of convergence. So you can generalize, this is also say that you can generalize consensus to this more realistic scenario where the links fail, and you can use the gossip algorithms for the communication and quantized noise and so forth.
What's in that?
Sorry?
What is in that?
Yeah, the condition is on the mean of the scale. It essentially collects the probabilities. Is like the Laplacian. except the non-zero entries are not the probabilities that the links fail or not. Okay, it's this little p. In the case where all the links fail with the same probability is p times the original L. So it's the average L.
What's the R?
Little r is the average. Little r is the previous average. It's this average. Okay, that's the mean of this theta variable. Okay. Okay, so that's to say, okay, you go. Now let's look at the problem that I really want to address now, which is, okay, so consensus is like this. If you have here a time scale, what consensus is operating on, so you have your sensors, and the sensors make a measurement, and then they iterate. And so consensus is assuming that the time scale at which the sensors communicate among themselves is very fast. Okay, it's very small compared to the sensing time scale. So they make a measurement, and then they take forever before they wake up and do another measurement. And in the meantime, they communicate. Okay? But suppose that now these two are at the same time scale. So you make a measurement, you communicate, but after you communicate, receive the data from your neighbors, you have another measurement. Okay, so you are not going to throw it away and wait for consensus to asymptotically converge. So you need to combine both, so you need to change, and that's what we call consensus plus innovation algorithms, okay? And you do that, and this is a pretty busy slide. I'll come back to it, because I first want to present you the structure of the algorithm, okay? So now you see it's not just like consensus. Consensus would be simply this term and that term with no y's times the x. Okay, that would be the original consensus. Then when we put back the noise, the structural noise, the failures and so forth, what we did was we put this term, forget about this tensor product, okay, for the time being, forget about that. Just L times X times the beta, which I previously called alpha, and then you'd have a noise term, okay, and you'd have a noise term. And now what we have is that you do some averaging. This is like averaging by consensus, but you also have to take care of the measurement. So the structure of the algorithm now is very different from previously, and what we have is, and now I'm going to do the analogy with the Kalman filter, but let me put all these things here. So what you have is you have the consensus part, okay, and you have what I call the innovations, okay, and this replicates the structure of the Kalman filter if basically this X was a local estimate of some random field that you are trying to estimate, okay. So what I'm saying is that the sensors now, say, are trying to estimate the temperature, say, some parameter temperature, okay. I'm not going to assume changes in time. I'm just assuming that I have a random field, no time varying, but spatially varying. And this is the current estimate at each local sensor, of, I'm sorry, I have to go to the previous slide, because I think that I set up the model here. So let me set up the model here. I wanted to give you the structure of the algorithm, but now I'm setting up the problem and I'll come back to that. So now what we have is a field that we want to estimate. The field is like a fancy name for parameter vector of dimension m, okay? And each sensor n makes a measurement of some of the components of this field here. So it could be 3 components out of 100, or it could be some averaging of component 3 and 5, and some averaging of 7 and 8. So this is locally available, okay? And I have some noise. And again, I told you that the H could be random, so it could be random, and the L is random, and there could be some quantization. Let's forget about all this. Okay, so the point here is that each sensor has a local measurement of some components of the field, but not all the components, okay? And then you have all that randomness involved. Okay, so this is now the solution, not the solution. This is the algorithm we propose to estimate that data, okay? So the reason why we have the tensor is that this X here is the stacking of the estimates at every sensor, okay? The estimates at every sensor of theta, okay? This theta is a vector n, so say sensor 1 will have an estimate of theta, and sensor 2 will have another estimate of theta. So I stack the two estimates of sensor 1 and 2, so now I have a vector dimension 2n, and then sensor 3, so 3n, and so forth. And so basically that's why I have this tensor. Okay, I have this tensor. If this was a scalar problem, if theta was a scalar, then n would be 1 and you would have the tensor. So this just to confuse you, I guess. So, okay, so the structure. So let me come back to the structure. This is the structure of the algorithm. Now, I make no claim that this algorithm is the best algorithm you have for a finite horizon. Okay, so no claims of that sort. But you could come up with a better algorithm.
What could it mean to be best?
Best, if you want to say, to minimize the mean square error at in 3 iterations. Okay, what's the algorithm? That when I process 3 times 3 measurements and do some local iteration 3 times, at time 3 has the least values. Okay, this is only asymptotically. The performance is only asymptotically. Now, the important thing, I'm not going to go through all the details of the math because that's not the point here. The important thing is to observe, to see this, that I have these two, alpha and beta, okay? And the alpha and beta satisfies the usual stochastic approximation type conditions, that the alphas have to go to 0, the beta has to go to 0 because this sum here is finite, but not too fast. Okay, not too fast, because they have to go out. But the interesting thing, as you will see, is that these sequences, to get really good asymptotics, these sequences have to be carefully crafted. Okay, you can just come here with any alpha that satisfies this condition and any beta, and hope that things are going to be fine. Okay. So that's the first thing I want to notice. The second thing I want to notice is that notice that I'm putting a weight on the innovations that is different from the weight I'm putting on the average. Okay, remember, this is the cooperation among sensors, this is the consensus type, and this is the effect of sensing. Okay, so here you pay a price of communications, here you pay a price of sensing. Okay, and you are combining at every iteration, you have a averaging, diffusion type of information, and you have an observation type of information. But what I'm saying is that you weight them differently, as it turns out, okay? And because you are going to weight them differently, this is no longer stochastic approximation, standard vanilla stochastic approximation, okay? And so proving the good properties requires you going away. So this is what's called a multi-scale type. Okay, so you have a time related time scale associated with innovations, you have different time scale associated with this. And it will be interesting to see which one should on. Okay. So which one should persist as time.
In practice, what are the examples for beta I and alpha I?
Sorry?
In practice, what would you choose for beta I and alpha I?
I'm going to show you. And that's what you need to be careful. Okay? Okay. And there is this other game here that you introduce, and this is kind of a degree of freedom that in the end, when you look at asymptotics, you say, well, now this is going to be nice, efficient, I'm going to converge. Now I'm going to compare my performance with the centralized, and then I want to, with this degree of freedom, you tune it to get the asymptotics of the centralized. Okay, so there are 3 things here. okay, to tune in this algorithm. One is this alpha and beta, these sequences, and then the other is the tuning of this K. Okay. And again, this was not derived from first principles, okay? This is just a structure that slap it on the problem and then see how it works. Okay, so what you would like in this distributed algorithm, what you'd like to show is these things like, is this unbiased? Okay, we saw that in the unbiased means does this converge to the mean? Does the mean of the estimates, does it converge to the true mean, for example? It's the unbiased. Is it consistent? Does it in probability converge? Do you get mean square convergence? Okay, and do you get asymptotic normality on your estimate? So these are standard conditions you like from your estimates, okay? And so you'd like to see if you get all of that. And then you'd like to compare the performance of the distributed to the performance of the centralized. If I can get the performance that at least asymptotically is close to the performance of the centralized, then you got something very interesting, which is you don't need centralized. Throw away centralized, no longer. You can have distributed solutions, and as long as you can pay the price of wait a little bit and pay a communication price, then distributed is, quote unquote, as good as centralized. Okay. I love it. Okay, now for these conditions to be possible, you need to go back to Kalman and Kalman-Bucy. And you go back and you see that they said, okay, here is my problem, here are my dynamics, here are my observations. I'm going to design a filter. But before I invest any amount of effort in studying my filter, I'm going to see if I have any hope of it being a nice filter. Okay? And so they said in their language, in their terminology, controllability and observability conditions, which are conditions of the model. You check them. They have full rank, those gradients that they construct. They are happy. They conclude the Riccati is going to be nice Riccati, it's going to converge, and it's going to converge to positive definite matrix, regardless of where I start. Everything's fine. Okay? So here, I'm trying to say, well, I want to study the properties of my distributed algorithm. I could jump into a computer and start simulations. I'm going to assume alphas and betas and k's and all sorts of things. And I spend, well, nowadays you don't need to spend too much, $500 in a station with 8 cores or whatever, but you spend all your time testing. That's not good. First, let's make sure that there are some structural conditions on the model that guarantee you that in fact you get performance. Well, it turns out that the structural conditions for distributed, to get conversions, to get those nice properties, the structural conditions are absolutely equivalent to the centralized ones with a caveat. So you have to have you don't need to have local observability. Local observability would be this gradient here to be full rank, to have rank capital N. You don't need that. So in the extreme case where your theta star has 1 million variables and you are only measured locally one variable, okay, you could not, just by processing your local observations, you could not understand what's going on the other 900 million variables, okay? But as long as, if you shipped all the data to a central fusion, and that central fusion could recover the state, okay, that's what I call my centralized observability, okay, this global observability condition. So as long as this happened, then the local is also going to be fine. Okay, so every local sensor is going to learn the whole 1 million variables. That's what I'm saying. Okay, but that you need to add another condition. So this is a condition on the model, and that's a natural condition. If the centralized cannot do the job, no hope for the distributed. The other condition, of course, is if you have a distributed problem, then the underlying connectivity has to be in some sense connected, okay? And again, it's a condition on the average connectivity. So as long as gossip, as long as you concatenate over time the links that are up and they form a connected graph, which is given by this condition, then the distributed will turn out to be as good as the centralized. Okay, so these are my structural conditions and the effective. And these are very natural conditions. We didn't have anything. Okay, so this sets up the assumptions, and I'm not going to go through them. They are all very reasonable. What I want is to answer the question that you asked. Okay, so what are my alphas and betas? Okay, well, here they are. The alpha has to go as a of I plus 1, so I is the time index, so it's like 1 over I to some tau, some power. Beta has to go 1 over I to some power. This A and B allows me to tune also things. But the taus, tau 1 and tau 2, have to go like that. Okay, have to go. So, what does this mean? The tau 2 goes with the beta, and the beta goes with the consensus, the diffusion. Okay? And the tau 1 goes with innovations. So what this means is that this power has to be larger than that power for things to behave. What does that mean? That means that the term of the innovations has to be weighted, the term of the measurements has to be weighted by a gain that dies faster to 0 than the diffusion term. Okay. If you think about it, it's reasonable. Okay, it's reasonable. So I had a professor that when he reached this stage, he would say, it's intuitively pleasing. The result is not intuitive, and it's pleasing. So it's intuitively pleasing. It's intuitively pleasing that this term here has to die out faster than this term. So you keep the sense, you sense and you diffuse or cooperate. But you better cooperate longer in a sense than you sense. And the reason is because of the measurement noise. Okay, the measurement noise. Okay. So each time you measure, you add noise because the measurements have noise. Okay. And if you didn't average out that noise, if you didn't average out that noise, so this term persisting longer or stronger than that, then that noise will take your variance. So that's the key.
You started the discussion by contrasting two cases.
Mm-hmm.
Second case where basically the sensing and the communicating were at the same scale.
Right.
Doesn't this condition kind of belies that?
No, what I was saying is that I make measurements, which is this Z, and I do my averaging on the same time scale. There are the word time scale is confusing, and I haven't yet been able to find another word. Okay, but what I mean by the same time scale of measurement of communication and sensing, I mean at every tick of the clock, when I communicate, I also make a measurement. That's that time scale. The other time scale is the time scale of this algorithm. Okay, and what this is saying is that I have a time scale associated with this alpha, and I have a time scale associated with this, and this has to be a faster one, it has to die out faster. Okay. Okay, under these assumptions, then you get everything you want. Okay, everything you want. You get everything you want. You get consistency, you get unbiased, you get variance matching the centralized estimator if you pick the right K, if you fine tune for those other degrees of freedom, and you get the asymptotic normality. Okay? You get everything you want. This variance here is this variance here, which is the estimate is asymptotically normal with the unbiased of the correct mean, and has a variance. This variance is a function of a gain that I had there in the structure, and now you optimize this to make this variance to be efficient, to be the variance of the centralized.
How should one make that?
Sorry?
How small you can make the variance?
Only to match the variance of the centralized. Okay? The centralized is Riccati, it's the usual Riccati with all the measurements stacked up, and you can make it. So you can make the distributed exactly asymptotical to perform as the centralized. And the other interesting thing is that the way you prove these results, and I don't think I have, okay, I have some remarks on the proof. Okay, if the alpha was equal to the beta, then it was essentially a stochastic approximation type algorithm, and the way you prove results with stochastic approximation, reminding you, is you go through the literature, you find the theorem, and that theorem has about 53.5 assumptions. Okay? And the only thing you need is to guarantee that you meet all those 53. You can drop to 0.5, okay, but you meet all of them. And so you craft your algorithm basically to meet those assumptions. To reverse engineering. You look for the assumptions and you craft. And that's what makes the alphas needing to satisfy some conditions. Unfortunately, when you go to these multi-scale algorithms, that doesn't hold. Okay? And so basically you need to prove some conversions. So you still construct a Lyapunov function here. Okay, so I'm sorry, this is kind of technical, but that's how in this you prove the convergence equation of Lyapunov, and you show that the derivative of Lyapunov, the gradient of Lyapunov on the dynamics of your algorithm, they remain essentially negative, so they have nice properties, and you'd like them to prove convergence. Okay, but to prove convergence there, because of the randomness, you have essentially to prove some nice behavior of that, and that's called the non-negative supermartingale and blah, blah, blah. Okay, so that departs completely from the stochastic approximation. Okay, so that's the key, and that's difficult in proving these results. Okay, I should make a comment here on the literature, because so algorithms, so I told you that if the algorithm was of the stochastic approximation type, then you essentially only need to fit the assumptions of existing results. When you depart from that to multi-scale algorithms like this, unfortunately, there are preliminary results. Workar has results. Sanjoy Mitter and Gelfand, a student of his in the late 80s, had results, departing different from the Workar results. Sanjoy was studying simulated annealing, conversions of simulated annealing problems. What Sanjoy and Gelfand and Mitter had was that one of the terms was already a supermartingale, or actually a martingale in that case, okay? And so they could build on the fact they had a martingale. In our case, we don't have even that the innovations term is even not a martingale, okay? And so you have to prove that. Okay, so we could not either use the results of Mitter and Gelfand. Okay, now I want now to enter my second part of the talk. And the second part of the talk is so up to now, I have a theta that is a parameter vector, so no dynamics. Okay?
Well, what happens, if I may ask you something? Everything here assumes that the topology of the node is fixed.
The topology, except the randomness.
Right. But the general consensus, by convexity arguments, is a three-line proof. Converges even if the graph structure is time varying.
But what you mean by time varying?
I mean that when you do the average of the neighborhood,
yeah,
the ni, the number of nodes you have is a time varying function. Everything can be time varying because I have a convex combination at every instant.
Yeah.
So you bound the upper bound, and
yeah,
you can show it decreasing every time step. You bind the lower bound from above, you show it increasing, and you get convergence. It just takes it in amount of time.
yeah.
And why I'm asking this here is because, okay, you can say in sensor networks, The only time variation may come from failures, but it can also come from things like sleeping protocols, non-sleeping protocols, in which the neighborhood can change in time. So can you extend that to that?
Yeah, so we actually, what we assume here is Gaussian. Okay, so as long as asymptotically you have a connected graph. Okay. And actually more than that, as long as a connected graph, and it doesn't matter how you visit your sensors. As long as you have that, then things work.
Even if I take what's called the union of the graph is connected.
Yeah, the union of the graphs.
But you take the union of the graph over a finite interval of time?
No, asymptotically.
Over the
If it's over finite, that's great. But I'm assuming over time. Yeah, over the whole.
Okay.
Okay, so now I'm going to go to a different one. I go back to exactly the problem of Kalman and Kalman-Bucy, so the centralized problem. So now I drop distributed because the issue I want to consider now, we also addressed in the context of the previous problem, distributed, but there are too many things involved and I want to focus on a particular point. The particular point is the following. I have my measurements there. So the dynamics are evolving, and I'm going to assume that every sensor or every agent, I'm sorry, this is centralized now, so forget about what I just said. So I'm going to assume that this is evolving, but the observer or the estimator doesn't always receive the measurements. Okay? What happens is that the measurements, say, go through a wireless network or whatever, packet switching, and packets drop at random times. And so sometimes the estimator has the measurement, sometimes it doesn't. So the measurements really are like a Bernoulli variable gamma t that multiplies the y of t. And when gamma t is 1, then the estimator has the measurements. And when the gamma t is 0, then there are no estimators. But unfortunately, this happens at random times. Okay? And so condition on the gamma t's, the problem is really like the old problem. And so you just apply the Kalman filter solution. But when you have the gamma t's, which are 0 or 1, so this is my observation arrival process, then the Riccati equation basically becomes random because this term here, okay, which is a nonlinear term in the Riccati equation, is affected by the gamma. So at some time t, if gamma is 0, then the p just follows so-called Lyapunov equation, so expands. Okay, expands because I have some estimate of the state, but I have no observations over a certain interval of time, so my covariance is going to expand. The error covariance is going to expand according to this linear equation here. But when gamma t is 1, then I can incorporate the measurements which reduce the covariance as we know. And so this p switches between what I'll call a Lyapunov type equation and a Riccati type equation. So you get into a dynamical system, P is a dynamical system because it's time dependent, and it's switching between two. So it's like I have two operators, F0 and F1. F0 is Lyapunov, F1 is Riccati. And sometimes I update with F0, sometimes I update with F1, and now we want to study this behavior of this.
You assume you know the instance of packet
Yeah,
numbers, right?
I know when by the way, this is a model that Sinopoli and Kenato and Franceschi, Jordan and Sastry, and I assume this is Sinopoli's PhD thesis. Sinopoli is a colleague of mine now at CMU. So this is the model they proposed, they studied, and what we are going to prove, and then we'll come back to compare and contrast with their results. So basically, this I'm saying what I just said, that I'm defining two operators. One is like a Lyapunov operator, so this is a linear matrix equation in X, and the other is like a Riccati operator. Okay, so when the gamma t is 1, I should have the gamma t there. I will apply the F1. Okay, and basically how the covariance is going to propagate in time is you start with a P0 and say, and then you propagate through, say that you didn't have a measurement. Then, well, if I have a measurement gamma 0, then if gamma 0 is 0, that means I have no measurement. Then the P0 grows to this value here. And if I have a measurement, then you will update the P0 with that equation. And then you move on. So each time you have a measurement, this is how you iterate. This is the sequence of iterates. Now, you'd like to ask several questions. The first question is, this, of course, is a random variable now, or a random matrix, okay? And this random matrix is in the cone of positive semi-definite matrices. It's evolving in the cone of positive definite matrices, because it's a narrow covariance, it's evolving there, okay? Now, can it go very far? Can it grow without bound? Of course, it depends on the gamma 0, okay? If the A, this problem is only interesting if the A is unstable, okay? If the A is unstable, and there are no measurements, then the P is going to go on, okay? And now what you want is, what Kalman says is that under the controllability observability, even if the A is unstable, the P is going to converge to a P spike, okay? So there is an invariant point, the invariant solution of the Riccati goes there. So what we'd like to know is, well, when I have and I don't observations, will this still stay in some neighborhood, in some neighborhood? Does it go very far or not? And so our results basically study this stochastic boundedness condition, and I'm not going to interpret all the P's there. I'm just going to say, is the P going to go very far or not? And here is a large number. Does the norm of the P go very far or not? And stochastic boundedness means with the probability 1, no, it will not go. So that's the condition we would like to know. So what is the condition on this Bernoulli variable? And since it's Bernoulli, the only parameter that matters is the probability of a 1 or a 0. What's the probability? What's the condition of that P or gamma bar? We call it gamma bar, the probability that gamma P is 1, which means probability that there is a measurement. What is the condition of that gamma so that this is true, stochastic boundedness? What's interesting is that the condition is, so here are the basic results. The condition is that this gamma bar has to be strictly greater than 0. So no matter how small, no matter how seldom do you receive measurements, as long as you keep receiving measurements with non-zero probability, things are not going to be bad. Okay, things are going to come back and stay in some neighborhood of the P star. Now the other thing that's interesting is that this P is, as I said, the covariance matrix in the cone of positive matrices. Okay, it's a random object, so it's wandering around. Okay?
What is gamma bar?
Gamma bar is the rate at which you receive observations. It's the probability of the Bernoulli variable. Okay, so if gamma bar is 1, that means I never lose observations. I always receive one observation. If gamma bar is 0, that means I never receive an observation.
Okay, but that's Bernoulli in your sense, the IID, right?
The IID, yeah. Okay. Every time the packet is dropped or not. Okay, yes.
Yeah, because we know the packet loss instance, could probably go to a more general model where gamma T is a stationary process, and it's the marginal of gamma T that doesn't play a role. So is it necessary to have a Bernoulli process, or can you go beyond?
We use the independence assumption of the gammas. So maybe we should revisit the proof and see. Okay, but we used the independence of the gammas. Okay, so the first thing is clear. Okay, as long as you receive from time to time observations that the things are stochastically bounded, so they don't go up to infinity. Okay, that's nice. Now, what Sinopoli and all proved is that as long as gamma is above a lower bound, okay, then the mean is finite. Okay, so we now say that actually we don't need a gamma as long as you don't want the mean to be finite. If you want the mean to be finite, you still need to meet the Sinopoli bound. But if you don't, if you are just happy with stochastic boundedness. Okay, now this one, as I was saying, you have this random object in the cone, okay? That random object then has some probability distribution in the cone, okay? What it's interesting is that this, as time goes to infinity, this is going to converge to a unique. Unique here means regardless of initial condition. So this is the equivalent, or the equivalent of the Kalman's result. Kalman says, if I always receive my observations, then this mu here is going to be a delta function centered at P star, okay? Because I have the Riccati converge to P star. What we are saying is, well, now it's not going to be a delta function because it's going to be random, it's going to wander, but it's still going to be regardless of the initial condition.
It's a monotone scheme, right? Gamma.
Yeah.
So that automatically gives you quite a bit.
Yeah. And you can characterize the support. I'm not going to go through this. Let me. This was some discussion. Oh, this is the last thing. Is we know that it converges. Okay. We know it converges. And then the last thing you'd like, as I told you, is the rate of convergence. Can I find the rate of convergence? And that essentially means rates of convergence and issues like that on these asymptotics on probabilities and so forth, you get what's called large deviation. Here we were a little bit fancy, and instead of calling large deviations, we call it moderate deviations because we use a slightly different way of defining the rate of convergence. But basically, what we show is that, so the gamma is the probability that you receive measurements, okay? So what we show, when you study these things, you need to consider what's called rare events, and rare events are the bad events, okay? So here is the P star. So this is in a one-dimensional problem. Here is the Riccati alla Kalman, okay? Of course, because you don't receive measurements at every time step, you can do better than that. So you have to have probability only to the right. You cannot have probability here, because then you're hitting Kalman. It would be like the zero, the perpetual motion. Okay, you can't have that. Okay, so the probability has to go to the right. And then to study these large deviations, what you say is this: let me consider a rare event. A rare event is something where you say, well, how far in probability was probability of this event that does not contain the P star, as this also goes as depending on where you locate this thing here. Okay, and what this says is that asymptotically, the probability of these rare events, these bad events, because you don't want this to be very far from this P star, okay? And you study as gamma bar goes to 1. So as the rate of measurements approaches the case where you don't drop any measurement, okay? And what it turns out is that you can get this as 1 minus gamma bar, and then you have to solve an optimization problem. Okay? You have to solve an optimization problem. But you can, it's an optimization problem, and at least we could solve for some cases. So let me just illustrate for a very simple case, and the very simple case is this. I have a scalar problem, okay, and it's an unstable. So because this we have a root of 2 is greater than 1, so this is the variance of this process is going to infinity. So I will need observations to keep it within bounds, and then everything is very easy. This is all unit variance, independent, blah blah blah. And my Lyapunov, you go through the equations. You write ax a transpose. So you get a square root of 2, you get 2, so you get all these things. This is the so-called Riccati operator, this is the Lyapunov operator, this is the P star, so it's the solution of the Riccati if I have measurements at every point in time. And now I have my gamma between 0 and 1. And the interesting thing is that if you look at the support of that invariant measure, the support looks like this. Okay, the support looks like this. Okay. So it's full of holes, okay? And this is zoomed this is zoom out, this is zoom, no, this is zoom in, this is zoom out. Okay? And what you see is that it replicates, basically the structure is replicated. Okay? So we didn't prove that the support of that invariant measure, we didn't prove it's fractal, but
Is it
it
fractal?
looks very much
It
like
looks, but is it?
I have no idea. Okay. We didn't prove it.
What are the implications?
The implications, well, let me say why we think we get this. So you are, first of all, this is a random dynamical system, which means I'm following this dynamics, and suddenly I have to follow some other dynamics, and suddenly I come back to this dynamics. Okay. The second is that the Lyapunov operator makes you jump, increases the variance. So if I'm here, in terms of variance, and now for the next few iterations I have no measurement, so I just follow my Lyapunov, so I jump from here to here, then to here, then to here. Okay, I go in jumps because it's that matrix equation. But now suppose I'm here now. Suppose now I have a Riccati. The Riccati brings you down, but doesn't bring you continuously. Okay, so you jump like that, and then you jump here, then you jump there, then you jump. And apparently, by doing that, you get these big holes, and inside you get these holes, and that's okay. That's the only intuition I have. Okay. It's the random dynamical behavior of the system. So, as I said, you have to. This is going to be this thing here. You have would like to study the probability of these rare events, the rate. You have to solve this thing. I didn't give you the details for that optimization, but in this scalar problem, you can actually find that it's equal to 4. So those numbers, the exponent after you solve the optimization problem goes as 4. So that dynamical system behaves asymptotically like 1 minus gamma bar over 4, when gamma bar approaches 1. So if gamma bar goes to 1, this measure here goes to a delta function. Okay? So if it goes to a delta function, the CDF, the cumulative distributive function, should be a step function. Okay? So as gamma approaches 1, you can see this is the P star. Okay, so this should be a delta function when gamma equals 1. The cumulative should be a step function. So as gamma approaches 1, you can see that you are approaching the delta function. Okay? And here is what the mode rate deviations tells you the 1 minus gamma bar to the power is. Okay? And so as gamma approaches 1, this should be the rate at which that invariant measure goes to 0. Okay? The probability of the bad events. And you can see that as gamma approaches 1, and this blue curve is obtained by Monte Carlo simulations. Okay, you do Monte Carlo, you can see that the gamma, as gamma goes to 1, the exponent of the measure of the probability of the rare event approaches the moderate equation. Okay. So when you are away, clearly you cannot be. So this should be monotonic, because as you get more and more measurements, you should go faster to 0. Okay? And so this gamma has to increase. It approaches that bound and it approaches this way. Okay, so this is all. And basically 50 years after Kalman. So my take to this problem is that you go to distributed, and when you go to distributed, you essentially fall into consensus type, but not exactly consensus. You have to take the measurements, and you have to consider all the randomness involved. And the randomness is not just randomness of communications, the usual communication noise, the additive noise. You have to consider the structural randomness, which is links failing. You have to consider other constraints, resource constraints like bandwidth, so you have to take that into account. But if you craft your algorithm in the nice way, you basically get that distributed can be as good as centralized. So that's, And when you also consider that you go to the filtering problem and you consider that you have these links failing, then you get into this packet loss, you get into intermittency, and then you get started this Riccati project. That's basically
Thank you very much. Questions? Yeah, I got that's one question. Suppose, okay, so you analyze the asymptotics of the Riccati equation. But you know that I can write the Riccati equation as an equivalent linear and do the analysis there and take the inverse of the two matrices only at the very end, just to get like the Riccati equation. Does it buy you anything or not?
I should actually ask that to you, because when I have a student and we need to study properties of the Riccati equation, that's always what I tell them.
Yeah.
First of all, go and look at the linear kind of solution, okay? And then we go, but unfortunately, those involve those phi matrices, right? The phi is like the system matrix.
Yeah.
You have those blocks, okay? And except for maybe scalar case and some random and some very well crafted two-dimensional problems, I could never use that. I could never make use of that. So I need to know how to handle that. So we attack the nonlinear problem. Now, let me say the following. What would happen, so you'd have two linear systems, okay? And what would happen is that one would be the Lyapunov and the other would be the Riccati. You'd still have dynamics that are switching between these two.
True, but because you write the Riccati as some gamma delta inverse, and then gamma delta satisfies linear equation of which you know exactly the dynamics, right? That'd be a lot easier to analyze than the nonlinear problem. That's the only thing I mentioned.
Yeah. Yeah, that could be a very interesting take on this.
Any other questions? Yeah.
May I try and take us out of the realm of pure mathematics into an application?
Sure.
Thank you. If we pull up that beautiful picture again with all the sensor nodes.
Oh, okay.
I'm envisioning, I'm an entrepreneur on campus. I'm looking at this picture as a radar system that's trying to, some kind of a MIMO radar system that's trying to determine what an unidentified flying object is doing. And you made an assumption, or you stated an assumption, that you're pretty much assuming away the communications burden. But in practical terms, if a radar network is to be set up in this manner, the communication burden of many nodes connecting to many nodes simply can't be assumed away. In fact, it may be the killing situation. So, and in which case a centralized solution may work out to be much better. So the question that I have for you is, have you looked at the communications burden of a central system versus a decentralized system, and what the implications of that on your conclusions might be?
That's a very interesting question, because that's exactly the dilemma that distributed problems will always face. Why burden with communication that is very expensive? Okay, communication is, if you look at sensing, at communication and local computation, communication, well, depends to whom you talk, but communication usually is assumed much more expensive than the two others. So why not? So there are several arguments that apply in some cases and don't apply to others. So one of the cases is, if you go to a centralized solution, you have, of course, a single point of failure. Okay, so in certain problems that's not a problem, in certain problems it is a problem. The second is that these sensors here, or these agents here, may have highly constrained resources, which means that going to this might be out of touch. They may be too far away from the center. Okay, so you'd have to do multi-hopping and so forth, which means now you make all the networking problems, and then at some point these would be saturated, or if they fail, or they would have to. So you want somehow everybody to be able to operate and carefully look at their own resources. So you don't want one start failing here and failing there, more or less. Okay, so that. And I had a third point, which I forgot. So I know that from a practical point of view, that's an issue. Why go centralized and not distributed? But that's the type of issues that we have.
Thank you.
Any other question? Why consensus in the usual sense?
I'm sorry?
Why combine the measurements in the usual sense consensus? Because from the point of view of combining the decision of sensors, that's the worst thing you can do. For example, I want to identify Tim over here from his fingerprint or his iris. I'll be stupid to average the iris detector with the fingerprint, because the error rate for the fingerprint would be 10 to the minus 2 versus the iris would be 10 to the minus 6. So if I average, I take a good sensor and I average with a bad one, and that creates problems. So could I, when I do the combination, compare the individual sensors and maybe pick the best or whatever? Is that possible?
Yeah, that goes back to the P, right?
Right.
So you look at your covariance, and there are terms in the covariance that are much better.
Because
than
you're
the others.
averaging, and this
Yeah.
is going to,
Yeah.
because you're averaging good and bad and whatever, and
That's
that's
true.
going to create problems.
So
I
you-
understand it makes the analysis feasible, but it's not exactly what somebody would do in practice.
Yeah, so that I think is a point very well taken.
Yeah.
And maybe what you should do is from time to time use the bad sensors.
But
and also
I'm
find use the
not
good ones.
offering this as criticism of this work, because nobody has done what I'm suggesting.
Right, I don't.
But
No, I
it's a question
understand.
that is occurred to me from time to time, even in our own
Yeah.
work with Theon here,
Yeah.
why would not do something like that?
Yeah.
That would be interesting.
Yeah.
Thank you very much. Any other questions? Let's thank you.